let me start this video with where I left over in the previous video. We were talking about natural numbers and trying to generalize a few formulas relating divisors, positive divisors of a number by taking up a few examples like 28 and 36. Let me take same example of 28 here as well. So 28 can be written as 2 square into 7. Let me write down the positive factors of 28: 1, 2, 4, 7, 14 and 28. So now what I'm trying to find, or what I'm interested in, is in knowing what is the product of all the positive factors of 28. So if you see, 1 into 28 gives me 28, 2 into 14 gives me 28, 4 into 7 gives me 28. Interesting. So if I say that I'm trying to say that there is a function pi of 28 which gives me the product of all the positive divisors of 28, it's nothing but it's nothing but saying that there are 3 pairs such that all of those pairs give me a 28. So this is nothing but 28 to the power 3. If you observe more carefully, it's nothing but writing 28 to the power total number of factors, which was 6, divided by 2. This divided by 2 is done to find the number of pairs. Now this was the case when my number was not a perfect square. Let me take an example of a perfect square as well. Let's say I take 36, which is written as 2 square into 3 square. So what are the positive factors of 36? 1, 2, 3, 4, 6, 9, 12, 18 and 36. 9 in number, right? So 1 into 36 will give me 36, 2 into 18 will give me 36, 3 into 12 may give me 36, 4 into 9 will give me 36, but I will be left over with this middle number, which is the square root of 36. So now if I try to find the pi of 36, I have clear cut 4 pairs which are giving me 36, so I can directly write 36 to the power of 4, and I am left with 6, which is nothing but 36 to the power half. So basically 6 can be written as 36 to the power half. So ultimately what I am getting is 36 to the power 4.5. Now interesting, if you see, this 4.5 is nothing but 9 by 2. And what is my 9 here? 9 is the total number of positive factors of 36. So in turn, it does not matter if whether my number n is a perfect square or not. In any case, I am kind of finding a similar kind of result. So when I'm trying to generalize these from these two, I'm trying to say that for any natural number n, the pi n, the number of the product of the factors of all the positive factors, the product of all the positive factors of n will be equal to n to the power of number of factors a plus 1 into b plus 1, so on and so forth, divided by 2. So it's immaterial whether n is a perfect square or not. In any case, the product of all the positive factors of n will be given by this expression. Now let me talk about another kind of numbers called coprimes or relatively primes. Both are same. Coprimes or relatively primes. Two numbers are said to be coprimes. Two number a and b are said to be coprimes if their GCD, or greatest common divisor, is equal to 1. In other words, coprimes and or relatively primes is the same thing. If two numbers a and b, two natural numbers a and b are relatively prime, then their GCD is 1. For example, let's consider 4 and 9. The only number common to that, the only factor common to 4 and 9 is 1. So GCD of 4 and 9 is 1, and that's why 4 and 9 are coprimes to each other. Now let's see. Let me have some space. Okay, so let me write 28 again. So as I said, let's investigate, the total number of coprimes that are less than 28. So when I say 28, 1 is a number that is coprime to 28 because the GCD between 1 and 28 is 1. 2 cannot be a coprime to 28 because the GCD is 2. Then I have 3, 5, 9, 11. Obviously all the primes other than the factors of 28 itself will be the coprime to 28. So the next number is 13, 15, 17, 19, 23, 25, 27. So let me count them on my fingers: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 coprimes that I got which are less than 28. So just observe one thing. If I add this first number 1 with the last number 27, what's that? It's 28. 1 plus 27 is 28. 25 plus 3, or 3 plus 25 is 28. 5 plus 23 is 28. 9 plus 9 is 28. 11 plus 17 is 28. And 13 plus 15 is 28 as well. Interesting. So what we observe is that coprimes of 28 exist in pairs such that each pair gives me the sum as 28, or the number itself. So let me generalize from here that for any natural number n which is greater than 2, number of coprimes less than n always exist in pairs such that each pair, the element of each pair, sum up to give the number n itself. So now let me say that I am interested in finding out the sum of all the coprimes less than 28. So we know that each of the pairs is giving me the sum as 28. So all that would be left for me to investigate is how many pairs are there. If I know the number of pairs, and if I know that each pair is giving me the sum as 28, I simply know the total sum, which will be nothing but. Before that, let me tell you that the number of coprimes less than a number is also known as Euler's number. Leonhard Euler was a great mathematician, who gave this Euler number with a significance that Euler number is a number that physically represents the number of coprimes less than a number. So let me denote Euler's number of 28 by phi of 28, and he said that phi of 28 will give me number of coprimes less than 28, and as we calculated, there are 12 such coprimes. So phi of 28 is 12. So how many pairs do we have? We have 6 pairs. So what could have been the sum of all the coprimes? Sum of all the coprimes would have been, let me denote it by s. So s of 28, sum of all the coprimes less than 28 would be the number itself, 28, into the total number of pairs, which is 12 by 2. So total number of pairs is 6. So this is the sum of all the coprimes less than 28. Now if I were to generalize this for any natural number n, I'm trying to say that for any natural number n greater than 2, the sum of all the coprimes less than n would be n into the total pair of coprimes. So the pair of coprimes will be given by the total number of coprimes, which is denoted by the Euler's number of n divided by 2. So I can now say that for any natural number n, the sum Sn of all the coprimes less than n is given by n into phi of n by 2. Now we'll discuss this phi of n in more detail. Euler's number basically was derived, the formula for phi n was derived by Euler, and it was represented by, if we say that n is, let's take the previous example, p1 to the power a into p2 to the power b, and so on and so forth. Phi of n can be given as n, the original n, into 1 minus 1 by p1 into 1 minus 1 by p2, 1 minus 1 by p2, so on and so forth. So this is a result which can also be derived. I will take up a video session in the future, and then I'll show you how we can derive the value of phi n, and in particular this expression. But for the sake of this session, let's only concentrate on the result here. So let's say, for example, 28. I am trying to find the phi of 28, which means the number of coprimes less than 28. So n is 28. What is my p1? P1 is, the first prime number is 2, so 1 minus 1 by 2 is half, into 1 minus 1 by p2. P2 is 7, so 1 minus 1 by 7 is 6 by 7. So all I get is 12 at the end, and you can match this up with what we already found manually. So this is the same as what we found manually, so this validates this particular formula as well. So now we can probably build up on this, and then there are theorems which come handy in finding remainders that's related to Euler's this formula. So this is something that we'll again take up in the later videos, but let's not shift our focus right here from the factors and divisors. So let's say I'm trying to write a n which is of the form 2 to the power a into p2 to the power b into p3 to the power c, so on and so forth. I've just changed the first number and replaced p1 by 2, and I'm trying to find out how many even number of positive factors does the number n has. So what would that be? No matter what, if I intend to find the number of positive factors of n such that they are even, I must include a multiple of 2 here. I cannot include a 2 to the power 0. It must start from 2 to the power 1, and it always must include at least 2 to the power 1 or greater power of 2 if it has to be a factor that is even. So so how many factors, such factors, do we have? The total number of factors, as we used to find out, was a plus 1 into b plus 1 into c plus 1. In this case it will be, we have 2 to the power variations of power of 2 from 2 to the power 1 to 2 to the power a, which are a in number. Powers of p2 can vary the way they used to earlier, so they can be b plus 1 in number, and p3 same case, c plus 1, so on and so forth. So the only thing that changes here is the first value. Instead of a plus 1, now we are writing a, because we cannot take a 2 to the power 0, because in that case, because all my rest of the numbers are odd prime numbers are odd numbers, only the first prime number here is the even number, I cannot take 2 to the power 0. So the total number of even positive factors, of n is given by a into b plus 1 into c plus 1, so on and so forth, where n is this. And how about finding out total number of positive odd factors of n? Very simple. Just subtract this expression that we got for even positive factors from the total factors. What was my total factors? For total factors would have been simply a plus 1 into b plus 1 into c plus 1, so on and so forth. Now I'm trying to subtract this from the total factors. So if you subtract, you will see that this part is common between the two, and I have a plus 1 here and a here. So subtraction will cancel the a, and we'll be left with b plus 1 into c plus 1, so on and so forth. So this is the number of positive odd factors of a natural number n. So this is very simple. Or in other words, the other way of seeing directly from the value from the expression of n, if I'm trying to understand what is the odd number of factors, if I do not want to subtract this from the total number of factors, how I can perceive it as, I don't in order to find out the odd factors, I will not include any factor of 2. I'll only concentrate on the powers of p2, p3, etc., and not concentrate on powers of 2. So in how many ways, what are the total number of ways, I will directly start with b, and I'll forget about this part. So I'll directly start writing b plus 1 into c plus 1, and so on and so forth, and that will as well give me total number of positive odd factors of n. So that's it for this video. I'll take up on the similar lines in the next video.